Can take it away. Um, so today we're going to be talking about fearless concurrency in Rust. I'm gonna share my screen before I keep saying anything. Are you guys able to see some slides?
Yep.
We're good. Um, yeah, so we're going to be talking about fearless concurrency and what it means to be fearless, or I guess what it means to be fearful of concurrency. Um, in different ways that's implemented in Rust. So, things we're going to cover today are, how to create different threads to run multiple pieces of code at the same time. We're going to be talking about message passing concurrency, which is when channels send messages between threads. We're going to be talking about shared state concurrency, which is where multiple threads share access to the same piece of data. And we're going to be talking about the sync and send trades really briefly. So one of the distinctions that the book makes is this concept of concurrency versus parallelism. So concurrent programming is when different parts of a program execute independently. Um, you can think of it as kind of like as a person multitasking, for example. Um, Parallelism is when different parts of a program execute at the same time. This is, you can think of as like delegating work to someone else and you're both working on two different things at the exact same time. For the sake of this chapter for fearless concurrency, it applies to both concurrent and parallel programming. So for the rest of this presentation, every time I say concurrent, it's concurrent and or parallel. Um, so yeah, I would, reading the chapter, it's they wrote it in kind of a funny way. It sounds like they wrote Rust's ownership rules for memory safety and then like didn't realize that it would also provide concurrency safety, but then they found out that it also provided concurrency safety and then they got excited. I don't know uh if that's actually how it went down. But that's kind of what I how I read the chapter, which I thought was funny. But yeah, so the ownership and type systems in conjunction with each other, they not only manage memory safety, but they also really help alleviate some common concurrency problems that are seen in other languages. Um, Doing this converts runtime errors into compile time errors. And I haven't actually written a whole lot of parallel or concurrent code in my past. But from what I gather, when you do run into runtime bugs in concurrent code, it can be very, very, very difficult to debug them. And beyond that, difficult to actually reproduce the situation in which the bug is occurring. So turning a situation where you reduce those runtime errors and have to deal with them up front during compile time, and or else your code won't compile, I think is a nice trade-off. And it also means, you fix your code while you're working on it rather than after it's been shipped. Um, this might mean maybe a bit more headaches and a bit more upfront time spent to actually make sure that, your code is written correctly. But it saves headaches down the road. So yeah, would they kind of discuss how like operating systems run different programs concurrently? So they run executed code, each program in a separate process, and multiple processes can be run at once. That's at the level of the operating system. At the level of the program itself, the program itself can also run its internal parts independently and concurrently. And that program can then decide, within the program, how to handle the concurrent running. Um, So, as in operating systems, each part that's concurrently running a program is called a process. In a program, features that run these independent parts are called threads. So for example, web servers have multiple threads to be able to respond to multiple requests at the same time and to not get blocked up if one service is requesting one of the making a request. So um yeah, so they talk about some of the so-called typical challenges of concurrency. So these are like challenges that other languages or other implementations of multi-threading or concurrent programs face. One of them is race conditions, which is when threads access resources in an unexpected or incorrect order. Um, uh, yeah. Another common challenge are deadlocks, which are where two threads are waiting for the other thread to finish, and so they end up in an endless deadlock waiting for the next one to complete its task, which prevents the program from continuing to execute. Um, and yeah, as I mentioned before, there's bugs that only happen in really, really certain and specific and particular contexts that might be difficult or even almost impossible to reproduce locally without the exact same, calling environment as where the bug was produced, and that can make it a really big pain in the ass to debug runtime errors. So shifting these errors to compile time saves you a lot of trouble. Um, yeah, not too much to say here. There's different types of thread models. So Rust standard library apparently uses a one-to-one model of thread implementation, which means that the program uses one operating system thread per one language thread. Um, Different crates offer apparently different implementations that have different trade-offs. I don't know what those different implementations are or what those trade-offs are, and the book doesn't go into it in too much detail. But just be aware that the standard library default one is one-to-one, and if for some reason you need to explore beyond that, there's crates to do so. Yeah, so without any more preamble, we can talk about how to actually create a thread in a program. Um, so creating a thread is pretty simple. You can create the thread using the thread spawn syntax, and you pass that to a closure. So the closure should contain the code that we want to run in that thread. So you can think of it as like passing that chunk of code into that thread to be run. Um, and when the main thread of a Rust program completes, so when the main thread is completed, all of the spawn threads are going to be shut down. Um, so we can go to a code example. Uh, I'm showing my full screen, right? Not just the
Yep.
one. Yeah, awesome. So we can have a look at what was it? So we can have a look at this two threads program. Yeah. So make this easier to see. So here's an example of like a really, really simple multi-threaded program. We pull in the thread crate, or sorry, thread from the standard library, as well as this duration type, yep. And in the main kind of body, we instantiate a new thread, or we create a new thread using thread spawn. Um, then this closure that started here and the code that's in between these set of squiggly brackets are going to be what we actually pass into this thread. And so we're passing pretty simple code. It's a for loop from 1 to 10 with some consecutive print statements and um, uh, this statement here, which causes the thread to just pause itself for 1 millisecond. Um, then that's the end. Oops, sorry. This is the end then of our kind of threaded code. So back on the main thread, we do a similar thing, except we're loop iterating from 1 to 5. Um, we print a statement indicating that we're on the main thread now, and we do the same thing where we cause this thread to sleep for a duration. So if we run this program, we see that this kind of oh, huh, this alternated perfectly, but I don't think it's done that before for me. Yeah, that's so funny. So that was a random random situation where it did alternate perfectly, but generally it doesn't necessarily uh do that. So kind of whichever thread is ready first is gonna execute its print statement first. It's not arbitrarily going to go from the spawn thread to the main thread. It'll be whichever thread is um, sort of ready to be picked up by the operating system at that time. So if you run it a couple times, you should see the order of these numbers and the pattern between which thread is called first and second changes. And also notice that um, the spawn thread never makes it past like 5, 4 or 5, right? Because it's getting canceled once the main thread has completed its for loop. So it's not allowed to continue on for the rest of its lifetime until 10 because this main thread is stopping at 5 iterations. Um, yeah, so that's kind of a really simple example of starting and using new threads. Um, if we want to change the behavior of all threads being despawned once the main thread is complete, we can use this thing called join handles, or we can join handles, I guess is the way to frame that. So basically what we're doing is we calling join on the handle will block the currently running thread until the thread specified in that handle is complete. And so this is how you can sort of force the main thread to wait until the initial thread is complete. Um, and it's going to unblock when the thread represented by the handle terminates. So we can have a look again at the code examples. Um, so if we look at this one now, it's a very similar uh, piece of code as before, except we're actually now naming this thread that we've spawned handle. Um, and then in our main thread here, oops, in our main function body here, after this second for loop, we call join on the handle specified here, which is the thread that we've spawned, and unwrap because it's actually a result. And so we're not handling errors here. We're just going to let it panic uh, if it runs into issues. And so if I now run that program with the join handles in place, it'll actually allow the 1 to 10 for loop in the thread to run to completion. So the main thread will still stop at 4, and then the spawn thread will run until it's done. And once this joined handle has completed, the main thread completes and it despawns all threads. But of course, the earlier thread has already been completed, so it doesn't need to despawn anything. And they made the interesting point that if you move this join handle up here, so what's going to happen here is we're saying we're starting this thread, we're giving it this for loop, and then we're saying wait until that thread is done before doing anything else, and then run the main thread, which is pretty much identical to not having threads at all and just having these two operations run in sequence. And so if I do that, we can see that now the spawned, oh man, Zoom is in my way. Anyway, um, we can see that the spawn thread is going to run 1 through 9, and then the main thread is going to run 1 through 4. Um, and so it's essentially like just running these for loops in series rather than in parallel. Cool beans. So that's about join handles. So far we've been talking about closures without um without transferring the ownership of anything within that closure. And so one thing you can do is use the move keyword, which we talked about earlier in an earlier chapter, and that's going to pass ownership to all of the data in that closure to the spawned thread. So what you're saying there, it's going to transfer ownership of the values it uses from the original environment into the thread that you spawn. Look at an example. So here, if we look at this, right? Actually, let's just do it like this first. Oh. So if I try to run this, and I can already see Rust Analyzer is, giving me troubles here. But if I try to compile it anyways, um, I mean, it's going to immediately tell me what to do, which is helpful. But uh, it's going to tell me that I need to force the closure to take ownership of V. And so if we look at the actual code again to see maybe why that's happening. So we're defining this vector here, 1, 2, 3 as V, and then um, we're trying to spawn a new thread and then run a simple print command on this vector. Now the issue is that this thread has no idea what's happening in the main thread concurrently while this is being called. And in particular, I could drop um, I could drop V here, right? And so because the program doesn't know when this is being executed, this thread might be trying to reference deallocated memory, and that goes against all things that are holy. And so Rust doesn't allow it. So what we need to do if we want to do something like this is use the move keyword for this closure right here. And basically what specifying that does is it says that, I'm not only spawning this thread and I'm passing it this code, but I'm saying that I want to move ownership of V to this newly spawned thread. So hopefully if I run that now, that'll work and it'll show that vector. So that's useful if you want to give full ownership of the code to the thread. And from what I read in the book, it sounds like the move keyword is pretty common, if not ubiquitous, in most multi-threading implementations.
Question, Jackson. I don't
Yeah.
remember if the book said this, but when you move transfer ownership with move, um, it's only going to be the values that like are actually needed within that closure, right? It's not, or is it going to pull in like the whole like functions environment?
That's a good question. I think it's I think it's all the values relevant
Mm.
in the environment that's being moved, but I'm honestly not entirely sure.
Okay, that's cool. Thank you.
Um, yeah. Alrighty. Cool. Yeah, so those are sort of some of the basic building blocks for setting up concurrent or parallel code. Um, and the book goes on to then kind of go into more detail about two specific kind of design patterns or paradigms for running concurrent code, or not running, but yeah, writing and setting up a really uh, data transfer between threads on concurrent code. One of these paradigms is called message passing concurrency. And so in that paradigm, threads communicate to each other by passing sort of streams of messages with data. And this is kind of a quirky quote from the Golang documentation, but it's do not communicate by sharing memory, share memory by communicating. I get the share memory by communicating part. I don't really understand the don't communicate by sharing memory part. I don't know. I don't know if it's like if that's a common saying that I should be aware of. But anyway, yeah, they recommend sharing memory by communicating. So that's what we're gonna try to check out here. So the way you set this one up is with a thing called a channel. You can build a mental model of a channel by literally thinking of a channel of water or a river, if that's the kind of example they used in the book. Basically, any messages that you place in one end of the channel will flow in a single direction all the way until the end of wherever that channel ends. Yeah, so that's kind of a mental model. Another extension of this is as we'll see in a moment, is you can have messages that originate from multiple different places, but all end up at a single endpoint. So the same model of multiple rivers ending up in the same lake can kind of be yeah, you can kind of scope that out using that mental model. So within channels, we have differentiations between transmitters and receivers. So, if I'm standing upstream at the river and I have a little boat and I write a message and I put it into my boat, I'm going to be sort of transmitting that message with the data that I want to send down the channel. And then downstream, there's going to be, you know, there's presumably going to be someone or something that receives that data and sort of reads the arriving message. And that's going to be, your receiver. And so um, a transmitter and receiver channel can be initialized with this MPCC channel function. MPSC is, oh man, what's the P stand for? Multiple producer, single, multiple. Anyway, it's the analogy I was just saying. It's the multiple rivers that that end up at the single receiver. So you can send messages from all sorts of different threads, but they all sort of end up getting sent to the same receiver. I can't for the life of me remember what those letters stand for.
Producer and consumer.
Producer and consumer. I don't know why. Yeah,
I
why'd they
had to
switch
look
from
that
transmitter and
definition.
receiver to producer and consumer? But perhaps there's a reason for that. Um, so we can go ahead and look at that one. So yeah. So yeah, if we have a look at this code, we're instantiating this channel here using MPSC, the MPSC channel function. And then we split that into a tuple of TX, sorry, rather a sender string and a sender type and a receiver type that both sort of take the string type as a argument is not the right format for that, but they wrap a string type. And it's apparently common to denote transmitters as TX and receivers as RX, or it's idiomatic rather. So we're gonna then spawn a new thread. We'll move the code or the values from this closure into that thread. We define some really simple message, and then the TX type has a method send, where we can send that value to the receiver RX, and unwrap it for to panic on error. And then on at the other from the other thread, we call the receive method from the RX type or from the receiver type to sort of to act as the receiving end of this channel, and then print out the value that we got from that. So this is a pretty simple sort of not concurrent example of that multi-threaded messaging system, but if we run it, we'll see, yeah, we'll see that it works. And so this string was sent from this transmitter across the thread to the receiver on the main thread. We can also look at sorry, one distinction. I'm pretty sure RX also has a type called try. Yeah, so there's also a type try receive. So the initial type, or the initial method rather, recv, will essentially wait. It'll block the thread entirely, and it'll just wait until it gets that message. And so if there's, for some reasons, I mean, if if this message is taking a very long time to send, this thread could be blocked for a very long time. And so try receive will immediately try to receive the message, and if it's not there, I'm pretty sure it's a result enum that it passes, and so you can build some kind of logic with a for loop and some delay to sort of periodically check if a message has been sent down the channel, and if it hasn't, you can continue on with further program logic and check again later on down the road. So receive and try receive are two different ways to um, build out your program logic. Yeah. So that's there's another example actually. 1 second. Yeah, there was. This is a more complex case of a channel or of concurrent programming using the message channel kind of paradigm. And so in this program, we did set up a vector of strings in the spawned thread, saying hi from the thread, and then we send each of these messages one by one with a delay, like with a second delay in between, and we let the interesting. So there's we actually iterate over receiver to print out the messages that it gets from this channel as it gets them. And so if we have a look at how that looks, we'll see each of these messages coming in through the channel with a 1 second delay in between them. The other type of concurrency that you can implement is shared state concurrency. So this one, instead of passing messages, multiple threads try to access the same shared data, the same data in memory. So before I go too much further with that one, the shared state, the reason people like this kind of message concurrency format is because it's generally easier to implement than shared state concurrency. With shared state concurrency, you have to jump through all sorts of hoops to make sure that whatever thread is trying to access that shared data is doing so in a safe way, and make sure that the thread that's accessing it isn't trying to access it at the same time as another thread. And you need the thread to sort of tidy up after itself once it's done accessing that shared data. So there's a lot more kind of overhead to make sure that you're cleanly accessing and organizing that data. So channel, like they made the comparison that channels are similar to single ownership, where they're just passing, they're just passing a data type down to a different place. Shared memory is a bit more similar to shared ownership, where you have to sort of check who is allowed to take out to access or look at that data at that time. Mutexes, which we'll talk about in a second, are the commonly used primitive for sharing memory between owners. And so a mutex is the name is short for mutual exclusion, and it basically is a type that allows only one owner to have access to the data at any given time. So it's a type that allows for multiple ownership, but it ensures that each of the owners is only accessing it one at a time. So it's mutually exclusively accessed. So to access data in a mutex, the thread has to ask to acquire the mutex's lock. So this is built into this data type, like this concept of a lock. The lock keeps track of who currently has exclusive access to that data. And so if the mutex denies this request to acquire the mutex's lock, it means that a different thread already has access to that mutex's lock, and thus has exclusive access to the data in that mutex at that time. So you can think of it as mutexes guard the data they hold with a locking system. What that means is that whatever thread does have exclusive access to the mutex at that time, once it's done accessing it, it has to remember to basically give the lock back, or other threads won't be able to access it. So they say, yeah, there's two main rules of mutexes. You have to attempt to acquire the lock before you can use their data. When you're done using the data, you have to unlock the data. So those are sort of the two key rules for using mutexes. So we can look at an example. Yeah, so here's a simple, quote unquote simple example with the mutex. So you can satiate the mutex type using the new function, or the new method, which is quite common for most types. So here we instantiate it with 5, and notice that you're never going to see the data type itself on its own. You'll never have just the I32. It has to be like a mutex of I32. That's basically to ensure that no matter who is trying to access that 5, they have to they have to undo the mutex first. They can never see the 5 without getting past this like mutex layer. I don't know if that's a correct mental model, but it's a way of thinking about it. It has to pass through this mutex to actually get at what's inside there. And so if I want to get at this 5, I take the mutex, I request its lock here. So I use this .lock method to basically make the request to say like, hey, can I acquire the lock for this mutex? And then, unwrap, because lock can, as a result type, that can give an error. So if the type that you get to after you've requested the lock from a mutex type is called the mutex guard. So this mutable num here, that is the result of m.lock.unwrap, is a mutex guard type. That's basically a type that can either be a value or it can be a denied. Like it can basically say, no, I'm not gonna give you the data because the lock has already been given to someone else. Um, and if that all functions well, I can update the number that's in that mutex. So I'll run that relatively simple example. So you see, I don't actually know what poisoned means. I'm sure it's something about the data security of the mutex. As you can see, this is already way more complicated than the message system. Um, but you can see that I've tried to update the number that's held within this mutex. I've updated it from 5 to 6. If I look at the mutex at the end of this operation, I can see that I have the mutex type and the data is equal to 6 as I hope I expected. Um, cool. So you can't you can't actually share a mutex type across threads. It's unsafe to do so. I I can't explain exactly why because I don't fully understand all of this, but you're not allowed to share mutexes between threads by default. Um, it's similar to the reference pointers that were discussed in the last call. And you also aren't allowed to share the reference counting type RC across threads by default. The only explanation there is for that is that there's memory overhead. There's overhead for allowing a reference counter to be shared across threads, and Rust it doesn't want that overhead by default. If you don't need it, why would you add that extra that kind of bloat? So the standard reference counting type is also not allowed to be passed between threads. This atomic reference counting type or ARC is allowed to be shared across threads. That's the takeaway at this stage. I don't really understand what atomic means still, but that's the main takeaway here. So we can just look straight up as how that's done. Um, so in this example, um, this counter object. So I set up a new mutex with a data value of 0 and I32. I wrap that mutex in a new atomic reference counter. Like the words I'm saying right now just sound ridiculous. So I wrap my mutex in an atomic reference counter. Um, then I'm gonna set up multiple handles. So we have a for loop here. I'm gonna sort of bump this counter. I don't even, honestly, I really don't even understand what what I'm trying to explain right now. I really tried to understand this last bit, but it's confusing as hell. Um, yeah, I I, I got nothing.
It's okay. It's okay. I think this chapter, like getting into this and like the last chapter on like smart binders are like
Yeah, I was good
tricky.
up until up until this stuff, and then I was like, this is just I can copy
Yeah.
the code, but I can't explain it.
I think it just the main thing with the reference counter is it just like keeps track of how many things want that like are using that value.
Yeah,
Um, so that way when like nobody wants it anymore, then it knows it can safely remove it, like drop it from memory.
deallocate it. Yeah, that makes sense.
Otherwise, it's gonna yeah. So let's you have multiple like owners. I don't know if owner is the right word, but it lets you have multiple owners because it's keeping track of how many people, how many obviously not people,
Yeah,
how many things own it.
Yeah, I mean,
yeah,
you
that makes
can't
sense.
pass in, you have to pass something that can be owned into the thread, right?
Yeah,
So you can't pass in the mutex because, as we saw before, once you pass it in, it's gone. Right.
right.
Um, so we can't pass in a reference to it because that won't work either, right? So we need to pass in one of these special smart pointers that can be owned.
No.
That's what I got. I tried like different variations. Like I thought there had to be a way you could just pass in a reference to the mutex, but of course you can think about it, there's no way it could ever work because you don't know when the thread could easily outlive the lifetime of that mutex, right? Otherwise, but now it won't because the mutex is in this arc. Yeah. I don't know. I probably explaining it much worse. But
I mean,
it's kind of what I got out of it.
better than I could. All that, I mean, all I understand is you're cloning this reference counter. You're able to pass a mutex into the thread, and then you're able to operate on that mutex once it's in that thread. I don't really know. Alrighty. So yeah, this is the last bit. Concurrency, you can extend it yourself. So the actual base functionality for concurrency in Rust is pretty there isn't a whole lot to it. And a lot of the concurrency sort of crates that you see are just extensions onto it that that you can build yourself for whatever purposes you need. And a lot of that is done using the sync and send traits. The send trait indicates that ownership of values of that type can move between threads, and the sync trait indicates that it is safe for that type to be referenced from multiple threads. Yeah, that's it. That's all I had for this presentation.
I did one of the experiments I did too is I'm like, there's got to be a way to pass in a